Welcome everyone. In this video lecture, we will solve a problem based on rectifier circuit, which is basically from the Microelectronics circuit books by Smith. So the question is, using the exponential diode characteristics means using the exponential diode characteristics means we have to use the diode current equation so that for Vs and V naught both greater than 0, Vs and V naught both greater than 0, the circuit of a half-wave rectifier has the following transfer characteristic. We have to prove this expression V naught equals to Vs minus Vd at Id 1 milliampere minus Vt ln V naught by R, where Vs V naught are in volts and R in kilo ohm. Note that this relationship, that is our V naught Vs curve, voltage transfer characteristic curve, by finding Vs corresponding to various value of V naught. So basically, first of all, we have to think in this question using the exponential diode characteristics. So exponential diode characteristic means we have to know the id equals to ix ex to the power vd by eta vt expression we have to use. Okay, say I am saying equation 1, and this is for the half wave rectifier. So this half wave rectifier is already shown here. Vs is supply, vd. So in this case, for the positive half cycle, okay, this diode will conduct, and the for the positive half cycle I am writing here, for positive half cycle, suppose we are saying this one is a sinusoidal signal. Okay, so for the positive half cycle, this diode will on, diode on. Okay, diode on. So in this case, the output voltage will be V naught equals to simply our Vs minus Vd. Very simple thing is that, means if some input like this, okay, for the first positive half, the output will be like this. Okay, but for the negative half, it should be 0. Okay, say this point is t by 2 t, very fundamental thing, so I am not. Okay, but this output v naught peak will be vs minus vd. Okay, we are not going to discuss this one. So this one is the important result, one important result for the half wave rectifier. Okay, so and we have to use the diode equation. Okay, because diode exponential characteristic. So first, in such problem, we have to think that what exactly we have to prove. V naught is a function of, so what exactly we have to prove? V naught we have to find as a function of Vs Vd at Id 1 milliampere. Just I'm writing, and also Vt term will be there. Obviously, V naught is also there in this one, and R. This function V naught is a function of these all terms. Okay, so that we have to find. Okay, so id expression, and here they have used id at 1 milliampere. So one equation is this: id equals to is ex vd by eta vt. Now what we are, well, first we are starting with id at 1 milliampere. So id expression is there, so one can easily write the id at 1 milliampere. id at 1 milliampere means this one is simply our 10 to the power minus 3 ampere. So this can be written as is exp. Now at that time the vd will be at 1 milliampere. The voltage across the diode at 1 milliampere, like vd at 1 milliampere. Okay, like this, at id 1 milliampere we can write by eta vt, ideality factor. Okay, we can uh, take one also, but okay, at the end we will do it. Okay, so now two expression is there, one and two. Okay, so what we can do, So here Vs is known to us, and if we find the Vd value, we can put in this expression. Say this one is a main expression, say equation A. So if we can find somehow Vd, then we can put in this equation and we can find the V0. Okay, so 1 and 2. So what we can do, 1 can divide 1 by 2. We can divide 1 by 2. So what we can write? We can write a simple ID, the main equation, by ID at 1 milliampere equals to Is x to the power Vd, the voltage across the diode, by eta Vt, all divided by Is exp Vd at Id 1 milliampere. Okay, write in like that. At 1 milliampere, Id equals to 1 milliampere, we can also write, okay, by eta Vt. Then after this Is and this Is will be cancelled out, and this expression can be written as simply Vd minus Vd at Id 1 milliampere, all divided by eta Vt. Simple calculation is there. Okay, or this expression we can write by this. So here in proof we have to find Vd. Okay, so what we can do now, what we can do, we can write Vd minus Vd at Id equals to 1 milliampere by eta Vt equals to ln Id by Id at 1 milliampere. We can write at 1 milliampere or at Id 1 milliampere. Okay. So now then after one more line I am to write, because we have to find the first Vd value. So Vd I am writing directly. This should be multiplied. So eta Vt into ln Id by Id at 1 milliampere. Okay, Id at 1 milliampere minus, okay, this should be Vd and this should be come here, so it should be plus Vd at Id 1 milliampere. This line is okay, means this value will be somehow Vd at Id 1 milliampere and Vd equals to eta Vt. Okay, so this one we have find. Okay, Vd we have find this Vd, because it is necessary, because we have to write the output function V naught as a Vs minus Vd. Okay, now we have to use that equation A. Now output voltage for a half wave rectifier, Vs minus Vd. Okay, so now what we can write, output voltage, that is our V naught will be Vs minus Vd. Now Vd we have calculated, so one can write simply Vs minus, okay, by putting this value, okay, putting the whole value, okay, in this. So eta Vt ln Id, okay, Vt ln Id by Id at 1 milliampere. Okay, so one more line, Id at 1 milliampere minus VD at ID equals to 1 milliampere. I'm just putting everything like this. Okay. So now what we can do, the same expression can be written as Vs minus Vd at ID 1 milliampere minus eta Vt ln ID. Okay, and ID at 1 milliampere. So ID at 1 milliampere means nothing but simply our 10 to power minus 3 means what we are writing. ID at 1 milliampere means this one is simply our 10 to power minus 3 ampere current. Okay, now we have to find the ID value because ID we have to find in the circuit. So if we are saying this one is a ID current, so ID current can be written as V naught by R. Okay, because this one is the resistance and this value will be plus or minus V naught and this should be our ID. So ID equals to higher potential V naught. Okay, so ID equals to V naught minus 0 by R. So ID is simply our V naught by R. So ID equals to simply our V naught by R. ID is V naught by R. So once again we can write minus VD. VD at ID equals to 1 milliampere minus eta Vt. ID equals to V naught by R. V naught by R. And the R it is given in the kilo ohm in the question. Okay. So we can write like this. So this should be cancelled out. So finally V naught equals to Vs minus Vd at ID equals to 1 milliampere by keeping eta 1 because in the proof it is eta value is not given, so we are assuming eta 1. So simply we can write Vt ln V naught by R. Okay, so basically this one is the final result we can say. Okay, so this is all about this question means we have to find the proof V naught. So how we have approached this one once again. So this one is the expression we have already derived this one. Okay, V naught equals to Vs minus Vd at ID equals to 1 in ampere and minus Vt by ln V naught by R. Okay, so first because the half wave rectifier is there, the V naught equals to Vs minus Vd, simply we can write. Then after ID expression is now ID at 1 milliampere. Then we have to divide and we are getting this expression. So VD is a function of this ID at 1 milliampere we have find. Okay, so now after V naught equals to this one from the half wave rectifier output voltage because our circuit is half wave rectifier, so V naught equals to Vs minus Vd. And after putting all these things and doing a step by step procedure, we can finally get this result V naught equals to Vs minus Vd at ID 1 milliampere minus Vt ln V naught by R. So this one is the expression voltage characteristics, okay, between the transfer characteristic Vs versus V naught expression. So this is all about this question. So thank you for watching this video.